Hi, I'm going to go through section 4 functions problem sheet 1 today. I'm going to start by doing something I normally do beforehand, but I'm going to click on section 4 functions. I'm going to hit Control C, then I'm going to go into solutions. I'm going to hit Control V, and I've got a copy of section 4 functions in my solutions repository. And the reason I've just done that is it occurred to me that I should be telling you to do the same. If you're following this course between January and March 2022, then this repository is being updated all the time, and it might be, if you want to avoid Git problems, e.g. because you don't know anything about Git, you might want to start doing the same sort of thing and making a new directory called My Solutions, and editing not the raw files that I'm editing in SRC, but editing things in a different directory. But anyway, here we are in the solutions directory where I type in My Solutions. Let's get the info view up, and I think we're ready to go. So this is relatively straightforward sheet. We're going to do functions, and what do you need to? We're going to talk about injective and surjective functions. So mathematically, it's sort of first year undergraduate stuff. So injective functions, there we go. You can see there's something called function.injective in Lean, and injective is a predicate on functions. So injective f is a true-false statement, and it's normally called function.injective, but because I've typed open function here, I can get away with just typing injective. You see, I could put function.injective here, there, and that's just kind of a bit of a mouthful. And then I could comment that out and it would still work, but you see that's just broken. So you see I've got a red line under surjective here, because surjective is called function.surjective. So you can either write function dot everywhere, or we can open function and then just talk about injective and surjective. So what's happening here? X, Y, and Z are sets. I mean, I've written types because Lean does type theory, but a type and a set are, they're both playing the role of a collection of elements. At this point in the theory, so you may as well think of a type and a set as the same thing, even though I know some people are kind of horrified by that sort of statement. As far as I'm concerned, a type and a set are the same thing for the purposes of this sheet at least. And I've got a function from x to y, and my claim is that f is injective if and only if for all a and b, f of a equals f of b implies a equals b, and that's the definition of injective, and so the left hand side and the right hand side are definitionally equal, and so that's why REFL works for this proof. And similarly, the definition of surjective, f is surjective if for all y there exists an x such that f of x is y, and the proof of that is REFL. And we're going to talk about id and comp as well. So the identity is a function. It doesn't have a docstring. Good old core Lean. The identity is a function from x to x, and id of x equals x, and the proof of that is again REFL, because id of x is defined to be x. So the left-hand side and the right-hand side are definitionally equal. And similarly, this theorem here, comp eval, if I've got f from x to y and g from y to z, and I've got an element of x, then g composed with f of x is just g of f of x. And again, the proof of that is REFL, because all of these things are true by definition. And so that funny little circle there, function.comp, I think it's called, there it is, function.comp, and id, and injective and surjective, we now have theorems that say exactly what these things are, and that's useful because even though they're definitionally true, we can use them for rewriting. You see, this is why they're useful. So what have we got here? We've got 1, 2, 3, 4, 5, 6 proofs. Okay, so let's do our proofs. Injective id. So if you like, we can we can work out what injective says. So we can rewrite, what was it called? Injective def. Yeah, we can rewrite injective def, and now you see that has unravelled exactly what the question says. For all a and b, id a equals id b implies a equals b. And now we've got id a, you see, and we've got a formula for id a, like we've got id eval. Maybe it's worth saying something about this. So now you kind of think, oh great, let's rewrite id eval next. Because that will change id a to a, right? So let's rewrite id eval, and I bet this is going to fail. Ha ha ha, it fails. Look, rewrite tactic fails. It says, I can't find id of anything at all. in the goal, and we're looking at the goal and like, come on, Lean, there is id of something. And the reason it's failing is this sort of technical limitation of rewrite, that it won't rewrite under binders. And this is something I've never mentioned in the course notes, so I should probably mention it now. So for all is a binder. So if I get rid of the for all, if I do intros A and B, and now there's no for all. Now you see it says it now rewrite id eval works. There we go. It changed id A to A. And if I do it again, it will change id B to B. So there's just a sort of a quirk of the rewrite tactic. But there's actually a beefed up version of the rewrite tactic called simp rewrite that does it. There you see that. So you could use the simp rewrite tactic, which does rewrites under binders as well. So there's several ways of getting around this. Well, I stick to the intros A and B, and then rewrite. Simp does repeated rewrites as well. So the other thing you could do is sort of simp only id eval, and that will probably do both of them at once. You see. And now we've got to prove that A equals B implies A equals B. So I guess we'll sort of intro H, or so maybe I'll say or rewrite id eval, that would work as well. Intro H, and now I've got to prove. So this is exact H. There. So there's the proof of that. There we go. There's some hints, but it's sort of worth noting that injective def is true, is definitional, right? So you can actually just delete it, and the proof still works. And id eval is also definitional, so we delete that as well. And the proof still works as well. You see, H says id A equals id B, but id A is defined to be A. And so this is exact H. And so there we go. And in fact, we could put those there, right? And then and now of course the bit that now I'm going to do something in term mode, and now I've had students asking me, are we going to be expected to write everything as short as possible? But intros in term mode is just lambda. So before the begin, like lambda A B H, comma H will prove this, right? There we go. So there's a proof which is shorter than the statement. If you're happy to do things not in term mode, maybe I'll get rid of that. There we go. Let's not intimidate my audience. Let's do surjective id. So let's rewrite surjective def. And so we've got to prove for all y there exists an x such that id of x is y. So let's intro y. And we've got to prove there exists an x such that id of x is y. So why don't we use y? And now we've got to prove that id of y is y. And one way, we could, refl will do it because they're definitionally true, but we could try rewrite id eval. That would also do it because rewrite id eval turns the goal into y equals y, and then rewrite tries a cheeky refl at the end. So there's one way of doing this. Now what have we got? Oh, we've got comp. Here we go. Injective. One of the main theorems of my first year introduction to proof course. So let's rewrite injective def at star. Let's have a look at what we have here. So HF says that F is injective and HG says that G is injective. And we've got to prove that for all A and B, if G of F of A equals G of F of B, then A equals B. So we could do some intros, right? Intros A, B and H. There. So A and B are in X, and we know that G of F of A equals G of F of B. And we want to deduce that A equals B. And so I guess HF, we could apply HF, couldn't we? The conclusion of HF is A equals B. So we can actually do apply HF. And now the goal has changed, right? None of the hypotheses have changed, but the goal has changed. I know, okay, what I want to do in this proof is I want to change the goal. I don't want to work on the hypothesis. I could try and work on the hypothesis and change it into the goal. Maybe I'll show you both. But I'm going to work on the goal and I'm going to change it to the hypothesis. So, and then apply HG. And now, and you see, I could, if you like, I could rewrite comp eval eval at H. There, and I could do it again, couldn't I? And now you see that hypothesis H is exactly equal to the goal, so now this is exact H. So there's a sort of completely gory proof of that. And now let's go down here. I mean, now let's golf it. We could get rid of injective def. That's never gonna. Oh yeah, I know what I was going to show you. I was going to show you the other proof, right? So we could. What could we do? We could do this rewrite compival at H thing. Oops. There. So now H says G of f of A is G of f of B. But HF says f of A equals f of B implies A equals B. And then G of, yeah, this is just, I need to do this apply fun thing. Apply fun, how does this work? Apply fun HG at H, does that, oh curses. What do I want to do? I want to deduce, oh I see, I need to feed hypothesis H into HG. Yeah, forget about that apply fun nonsense. So refine, what is it? No, it's not refine. It is specialize HF underscore H. Nope. HG underscore. There we go. That's going to work. I'm finally there. So now HG says that f of A equals f of B, and I want to feed that into HF. So specialize HF underscore H. Oh, I'm quite surprised. Ah, that needs to be HG. And now HF says that A equals B, and so it's exact H. F. Oh dear, that was a bit ropey, wasn't it? But there we go. There's a proof. Those underscores are a bit of a shame. Why were the underscores there? HG is expecting an input. It expects an input of A and an input of B, and then an input of a proof that G of A equals G of B. So in fact, we could fill in these. You know, this would be f of A. Oops. And this would be f of B. We could fill in the holes if you like. But one sort of interesting thing about this is that H, once Lean knows, it's sort of a bit ridiculous. It's a bit ridiculous that these are in round brackets, and that's my that's a consequence of injective def. If you actually, let me show you something. Like instead of rewrite injective def at H, if I remove that, oh, removed it from the wrong one. If I remove that from here, this proof's going to break. Yeah, there we go. Let me show you. If I unfold injective at HF, let's unfold it at HG. You can see that actually these inputs A1 and A2 are in those squiggly brackets, and the squiggly brackets mean Lean's going to figure out what those are from later inputs. So now I'm going to put specialize HGH. There's a lot more going on in this video than I was expecting. And so there you go. And now HG has become f of A is f of B. And similarly, I'm going to do this, aren't I? There. So there you go. There's some. Let me maybe explain in a little more detail what just happened then. The actual definition of injective involves squiggly brackets, and the idea about the squiggly brackets, they're not normal round brackets. You see, here we have normal round brackets. Here we have these squiggly brackets that mean these are actually inputs of the function, but Lean's going to work them out for you. And so, for example, what's going on here is that HG, it wants two inputs of A1 and A2 in Y, but it says it's all right, I'll work them out. I need them as inputs, but I'm going to supply them. Just you tell me the next thing. And the next thing it wants is a proof that G of A1 equals G of H2. So we feed into HG a proof that G of f of A equals G of f of B, and then Lean figures out that A1 must be f of A and A2 must be f of B. So Lean works out those inputs itself and doesn't bother the user at all. So there we go. So we can specialize it. In fact, we can probably do. Oh, I'm off again. Does that work? There, we don't need to. Oh, in fact, we could probably do. There's no point even once we've done all this specializing. The hypothesis becomes exactly the goal. So we could probably just do this. We could do exact this. There we go. And I suspect that we don't need the compivals, and we won't need that. So there you go. So there's another proof. So it's lambda ABH HF of HG of H. There's the proof of that. which is kind of nice. Okay, sorry, that was rather a digression. So what's this going on here? So surjective, I know what surjective means. It means for all g composed with f, that's a function, I can click on it, right? G composed with f, it says, it's a function from x to z. I clicked on it and it told me its type. And the type of g composed with f is the type x arrow z, which is the type of functions from x to z. G composed with f is a term of that type. And so what does it mean for that function to be surjective? It means for all z there exists an x, right? So the proof of that can start intro z, because I know, you see, I could do unfold surjective if you want. There, you can see it. Or I could do rewrite surjective def. That would also do the same thing. There, because I defined surjective def up here. There it is. Or I could just do none of those things. I could just do intro z. So I've got to prove that there exists an x such that g of f of a is z. So where's that x coming from? I mean, that's a good question. Sorry, where's that element of x coming from? And I guess we have something in z, so by surjectivity of g we get something in y. So maybe I will rewrite surjective def def at hg. And now you can see hg is a function, right? It eats an element of z and it spits out a proof that there exists an element of y such that g of it is the element of z. And so we could specialize hg at z, so i.e. feed it the z. And now this hypothesis hg says there exists an element of y such that g of that thing is z, so we can get it out with the cases tactic, right? If you have exists in the goal, you use the use tactic, right? We really want to do use something at this point. Right, that's how we're going to make progress with that goal. We're going to say use some element of x, but there's no element of x in sight at this point. That's the problem. But there is an element of y which is tantalizingly close. We just have to extract it. Hg says that one exists, so let's do cases hg with yhy, and we've got it out. There it is. There's the element of y, such that g of y is z. And now but we want an element of x, and so we just do the same thing, right? We do cases. I can just do it cases hfy with xhx, and then use x because that's the x we wanted. And now we know. You see, now we've got a g of f. We've got to prove g of f of x is z, but we know that f of x is y. We know that g of y is z. So we just have to put everything together. And I guess you should be lazy and use a tactic. I don't know. Finish will probably do it. There we go. So use some high-powered tactics that solve some basic logical things, or we could just do it the slow way. We could rewrite comp eval there. So now that's become g of f of x equals z. So now we want to rewrite hx. So we could do all this in a big line, couldn't we? We could rewrite hx as well. And now we've got g of y is z. So we could rewrite hy, I guess, while we're here. I mean, we could do exact hy, but we may as well just rewrite hy, because then rewrite solves the goal for us. So there's that. And again, I feel like I want to golf it. But I'm not going to need that rewrite surjective def. This case is hg, so I don't need to specialize hg at z and then do cases hg. I could just do cases hg of z. And then hy says that g of y is z, but z is just some arbitrary element, so I could do r cases. I could use the refl trick with y, refl. And now there's no z's in sight. You see, that's so this is sort of, we've done more steps more quickly. You see that we used to have a z in the goal here, but that's gone, right? The whole point about, you can see in this proof up here, hy was the proof that g of y was equal to z, and right at the end there we still had this hypothesis that g of y was z, and we were carrying a z round here. But what I'm saying is, why don't we just, like, z is equal to g of y, and that's what we want to use. So why don't we just say, why don't we just sub in, right? Wherever we see a z, let's replace it with g of y. So this refl here is what's going on, right? We're defining z to be g of y. This isn't some type theory. I mean, this is just a hack, right? This just means you can't name a variable ruffle, right? There's something fishy going on there. And then we're going to do just the same thing here. R cases hfy with pointy brackets, x comma refl. And then we're still going to use x. Oh, then there we go. That does it completely. And in fact, one could do. I guess one could do. If you, I mean, that'll do. Use x is short. That's pretty cool. Solving the goal with use. The reason it's why did it solve it? Let's hover over use. Use will instantiate the first term. It will then try to close the goal. It tries to close the goal using triv, and triv tries refl. That's what's going on. I think we could do exists x. That's a sort of a more primitive version of use that doesn't try refl. And now refl would work here, but I guess triv. Yeah, what does triv do? Yeah. So it tries to solve the goal by reflexivity. So that's why use is solving it straight away, because use tries triv and triv tries refl. So there's a shorter proof. But this would be harder to do in term mode. We could do lambda z, that would be okay. We could sort of do it half. We could do lambda z, comma, and then we don't have to do the intro z. But this R cases business, we're essentially doing rewrites here, and rewrites are hard to do in term mode. So this proof is definitely better done in tactic mode. Okay, so those are the proofs of some theorems which were in my first year introduction to proof course. And now we've got some of the questions on the problem sheet. This is the first question on the functions problem sheet. We've got f from x to 1, g from y to z, and a hypothesis that g composed with f is injective. And the actual question on the sheet says true or false, is f injective or not? And the answer is it is true. So let's try and prove it. So let's do intro h. So we want to think about this proof. Injective is also, we could do intros. We do intros h, f, and then we do x1 and x2. And then there's probably a hypothesis as well, h1, 2. Right, and now what does injective g composed with f mean? Look, this is a great example. Mathematician floundering around because they haven't done what they're supposed to do, which is work out the proof on paper first. I mean, h says that h is also a function that's expecting some inputs. I could rewrite injective def. At h, sorry. And now h is expecting two elements of x, so I could just feed them in, right? Specialize h, x1, x2. Now we can see what we've got. And now h says g of f of x1 is g of h. The conclusion of h is that x1 is x2. So we can actually apply h. In fact, we might have been able to apply it right back here. Apply h. There we go. Yeah. We could have got away with that very early on. We're applying h, and it says g of f of x1 is g of f of x2. So maybe we should write, what was it called? Compeval or something. Yes, compeval. There, g of f of x1. Actually, we only need to do it once. Let's see if we can get away with just doing it once. Because now we've got an f of x1 in the goal, and we've got this. So now we could rewrite h1, 2. Now will that do it? There we go. So there you go. That's absolutely not how you should do mathematics in a theorem prover, because I didn't make any attempt to try and work out what the question was. I just followed my nose. And do you know what? I'm going to do the same. It's anarchy. I'm going to do the same thing here. I'm going to do intro h. And now I've got to prove, I'm going to do intros h. Surjective g means for all, so there's a z. And now I've got to prove, I haven't got a y. So I need a y from somewhere. And the only place I'm going to get a y is from h. So what does h say? H says that some map from x to z is surjective. So I'm going to do R cases. H of z with x, comma. I'm going to put hx. Do you know what? I'm going to put refl. And now you see, so I need an element of y with some property, but I have an element of x, so I can use f of x. And there we go, and it worked. And I suspect if I hadn't done the refl trick here, if I'd done hx here, then use fx, so you see it doesn't work because I've got to use exactly. Then this would be exact hx, right? there. So in fact, when use then exact, I could probably do that with. Use is the same as refine, right? Refine point is f of x comma something. There, and then you see the goal exact. Yeah, so I could put hx there. But there we go. This is quicker, isn't it? But you see, then I don't. Anyway, and then use fx. That'll do. Oh, that appears to be the end of the. Having so much fun, I didn't notice I'd finished. There we go.